Before we begin talking too much about thermodynamic relationships, I wanted to take a brief moment to give you an overview of thermodynamic functions, which we've begun to learn about during the course of this module. Now, we started off by talking about physical properties, and those included things like pressure, volume, temperature, and even the amount and the number of moles. So these are all interrelated. So I'll call these all interrelated by the equation of state. So if you know the equation of state, you don't need to know all of these things at once. You can know all but one of them, and the last one can be determined then directly from the equation of state. But along the way, we've also introduced some other things that are basically functions of these physical properties. And those are things that I'm going to call thermodynamic potentials. They're basically energy functions, and we haven't spoken about them too much as functions yet, but we will as time goes by. Those include the internal energy and the enthalpy, and those in effect are energy functions that will be our prime focus of study. Now, we've noted that we have also other energy quantities. For example, if we multiply pressure times volume, that's an energy quantity. R, the gas constant, times temperature, that's an energy quantity. So these have units of energy, but they are not thermodynamic potentials, and they can't be treated in the same way as potential. They're basically they're quantities with units of energy that are related by the equation of state. And I'm going to abbreviate equation of state as EOS. All right, now when I talk about the thermodynamic potentials, I'm going to mean functions like U and H. These are the first two that we've encountered in this course. We're going to find two others later on in Module 3, so stay tuned. But for these, what I want to do is think about what kinds of functions they are. And in particular, I will say that U and H can be written as functions of these thermodynamic physical properties, such as pressure, volume, and temperature, but I'm not going to write them as so much as a function of the quantity. And the reason for this is I'm going to introduce molar quantities for these functions. So in other words, the amount of energy that might be in 1 mole of a substance. And so these molar quantities are basically going to be the internal energy divided by the number of moles, or the enthalpy divided by the number of moles. So another way of thinking of this is that the full internal energy is going to be the number of moles times this molar internal energy, and the full enthalpy will be the number of moles times this molar enthalpy. This notation of a bar over the symbol is I'm going to use exclusively now for molar quantities. So if it's a function that has a bar over it, that indicates that it's a molar quantity. Now, when I look at the physical properties that we've introduced, so I'm talking about P, V, and T, I will note that P and T are intensive properties. In other words, they do not depend on the amount of stuff that you have. Every fraction of the system will have those same pressure and temperature. But the volume is one that does depend on the amount of stuff that you have. So we're going to introduce a molar volume by putting a bar over that. And that's just going to be the total volume divided by the number of moles. All right, so this will allow us now to rewrite our equation of state, for example, for the ideal gas. We'll be able to write it now not as PV equals nRT, but instead as PV bar equals RT. That will simplify it a little bit. Now, I've been awkwardly explaining that we would write PV equals RT, and that meant that we were assuming there was 1 mole. Well, now by using the molar volume, we don't have to worry about that assumption anymore, but we can scale everything by the number of moles. I have one further comment to make, and that is, again, to emphasize that these two quantities that we've talked about, heat and work, are exchange mechanisms. They are interactions that allow for the flow of energy between system and surroundings, for example. We know that the heat is related in some way to the temperature, and we've talked about work primarily as mechanical work, so PV work, so I'll call that mechanical. But there are other types of work. For example, we could have electrical work, and we'll talk a little bit about electrochemistry when we get to Module 6. There also could be magnetic work that's done. We're not going to be talking about these so much in this course. We're mostly going to be focusing on PV work just because mathematically it's a little bit easier to deal with. But I want you to be aware that these other kinds of work do exist, and they can come up in different kinds of applications. All right, so hopefully with this overview, a lot of the other things that we'll say in this particular lesson will make a little bit better sense.